The most versatile node is undoubtedly the Voronoi texture. It allows you to create organic, sci-fi, abstract, and so many more types of textures all within one single node. It has so many different settings, so in today's video, we're not only going to explain what every single setting in the node does, but we're also going to take a deep dive into the math and the logic behind this particular texture, which helps create your favorite animations and games. So whether you're a seasoned Blender user or an absolute beginner, or even if you're not an animator and you're just curious about how different games are made, this video will have something or the other just for you. It's going to be a pretty long one, but it's definitely worth the ride. I learned quite a lot while researching for this video, and I'm sure you'll learn something too. With that, let's go ahead and demystify the Voronoi texture. To understand the Voronoi texture, the first thing that you need to know is what exactly Worley Noise is, because the Voronoi texture is based off of the Worley Noise algorithm. To understand how we can create Worley Noise, let's go ahead and create a grid which is actually going to represent every single pixel on a screen. So every box in this grid is actually a single pixel, and we have to determine what color or what value the pixel is going to be based on the algorithm. So let's start by going ahead and distributing a bunch of points randomly in this grid as shown. Now for every pixel, we're going to calculate the following. So let's assume that we take this pixel over here. The first step is going to be figuring out which is the closest point. So from these three, it seems like this point is the closest. So once we figure out what is the closest point, we then have to figure out what is the distance between the point and the pixel. Once we figure out that distance, we light up that pixel with that exact brightness. Remember, the brightness of a pixel can be any value ranging between 0 to 1. So as long as the distance is really close, like this pixel over here, the distance is going to be very less, so the value or the brightness of that pixel will be really low. As we go further and further, because the distance is increasing, the brightness is going to keep increasing, and then it'll keep increasing until we reach a point where the closest point becomes another point. So maybe it's going to keep getting brighter and brighter and brighter till about this pixel, where the closest point now becomes this particular point, after which it's going to start reducing in brightness till it becomes absolutely dark or black over here. So every single pixel is going to be calculated and a brightness is going to be attached to it. So let's go ahead and find out what it looks like when we attach every single pixel with a brightness value like that. This is what it will finally look like. Now, of course, we can go ahead and just hide the points to see what the texture looks like. And this is what Worley Noise actually looks like. It's a cell type look which has fairly smooth gradients between them. And this is the basis of the Voronoi texture. If we switch off the grid, we get an even better representation. As we increase the resolution, we would get a smooth plane that looks something like this. And this is the true Worley Noise. Now that we understand what Worley Noise is, we can actually start breaking down the Voronoi texture. So if we were to take a look at the Voronoi texture node, we can see that the node is made up of three different types of options. We have the outputs over here, and then we have the properties, which are these four options over here, consisting of three drop-down menus and one Boolean checkbox. And then we have the various input parameters that we can also control. So the base operation is always going to be creating Worley Noise, but we're going to be changing the properties or the way the noise is created or calculated using all of these different options. So with that, let's go ahead and start understanding what each of these outputs actually do. The first output is the distance output, which is what we are actually seeing right now. So the entire explanation that we gave, where each pixel gets the brightness based on the distance, is actually the distance output. But we still have two other possible outputs. So let's understand them one by one. Now, back to just having these different points, imagine instead of the points just being white or black, let's give each point a different color. So by doing this, we now have every point with a unique color. So this point is green, this point is reddish, this is purplish, and so on and so forth. So the random distribution of points have a random color as well. Now, for every pixel within the grid, instead of calculating the distance to the nearest point, what if we took a pixel, found out what the nearest point is, then checked for the color of that pixel and colored in that particular pixel as that same color. So all the pixels that are nearest to this particular green point will end up turning green. Similarly, all the pixels that have this particular purple as the nearest point will end up becoming purple. If we were to do that for every single pixel, this is what we finally end up with. So if we were to just zoom in, you can tell that any pixel is closest to which particular point. Since this is orange, it must be closest to this point as compared to this particular point. And that way, every pixel is going to be lit based on the closest point and the color of the closest point. If you were to remove the grid, this is what it looks like. And of course, if instead of seeing each pixel so large, we see it in a fine distribution, this is what we get. So this is the color output of the Voronoi texture. And this gives us a flat cell-shaded look without the smooth gradients as we were getting from the distance outputs. That leaves us with one more output, which is the position output. That's also very simple to understand. Let's go ahead and take a look at just the points once again. This time, instead of the points getting a random color, let's give the points the color based on their location. What does that actually mean? If we switch on the grids, you can see that the x-axis has a red value and the y-axis has a green value. As you know, every pixel should have a color value with 3 different parameters: a red value, a green value, and a blue value. These 3 numbers together make up a single color, or the color of each pixel or point. Now, if we assume the x-axis value to be equal to the red and the y-axis value to be equal to the green, and maybe the z-axis value, which is going to be in the 3rd dimension like this, if this particular value becomes the blue values, then every point can be given a unique color based on their location in 3D space. So just like before, let's go ahead and create the grid. And when we have the grid, you can see that there are points present in this 4th quadrant as well. However, they're completely black because both the red is in the negative and the green is in the negative, and the negative values are clamped off at 0, so these just have a value of 0, 0, 0, which is completely black. And also, as we go towards the right and the top, which is the 1st quadrant, we get yellow because in the additive space, red plus green, if you have positive values for red and positive values for green, you get yellow. So now if we were to take each pixel, find out the closest point, see the color of the point, and then shade in that pixel the same color as that point, you would get a distribution that looks like this. So hopefully this gives you an idea of what the Voronoi shading gives when you use the position outputs. Remember, this is in 2 dimensions. If you were to add in the 3rd dimension, you could get completely different values, with some areas being bluish as well. But all of that is a topic for another video. For now, hopefully you understand what each of the different outputs of the Voronoi texture actually creates. So that should form the basis of the Voronoi texture outputs. Now we can finally transition into the properties of the Voronoi texture. The first thing that we need to note is that right now, the example that we've shown, every single cell has an absolute dark point present. Now this dark point is because every point is present on this particular plane, and as we go closer and closer, we will eventually run into pixels that intersect with the point. And because it's intersecting with the point, the distance is going to be 0, so the brightness of that pixel is also going to be 0. So every single cell is going to have an absolute dark spot with a brightness value of 0. And that is because all of the points are being distributed only in this plane, or they're being distributed only in 2 dimensions. So because they're being distributed in only 2 dimensions, you get this black dot. If we were to change this from 2D to 3D, you would notice that many of these cells no longer have that dark spot. And that's because these points are no longer distributed only on the plane, but they're being distributed in 3 dimensions. So the closest spot to maybe this cell may not be present right here, but could be present just above, maybe somewhere there. So because the point is present over there, there is some distance between the pixel and the point, and that is the brightness of this particular pixel. So that is what 3D does. However, you should note that when this is set to 2D, in the mapping, you can go ahead and move the texture as much as you want on the Z direction, and you're not going to get any change because the distances are also calculated only in 2 dimensions. The distance in the 3rd dimension is completely ignored. And because of that, you can move this on the Z-axis as much as you want, but all the points are going to still remain exactly as is. However, you can move these on the X-axis and Y-axis to get them to move just as shown. On the other hand, when you change this from 2D to 3D, you'll notice that moving it along the Z actually causes it to shimmer or change like this. And that's because the points are actually moving through 3-dimensional space and intersecting with this plane and continuing onwards. So the distribution of points are random at every single stage, and as they move through, they intersect with this plane in different ways. And that is what causes the points to appear and disappear. Every time you see a new cell being formed, there will come a point where a black spot intersects with that particular cell. And then soon enough, it goes away. Then a new cell will be formed eventually. And once that cell is formed, you will see that there is some point where a black dot is formed. So that shows how these points are moving through three-dimensional space through this particular 2D plane, causing this particular texture. However, we don't stop at 3D. Blender also allows you to calculate this in 4D as well. Now that would confuse a lot of people because in the fourth dimension, by moving this W slider, you get the exact same effect as you were actually moving in the Z direction. So you can see there's almost no difference between moving in the Z dimension as well as the W dimension. And that is actually because Blender does not restrict you to create 2D textures. You could use this Voronoi texture in 3 dimensions. For example, let's go ahead and take a look at this particular object. This object is being created in 3 dimensions based on a Voronoi texture. So as you can see, the points are actually distributed in 3D space, and all of these points that are within a certain radius of the Voronoi texture points, or the randomly distributed points by the Voronoi texture, are being visualized just like this. Now you can continue to move the points in the x-axis just like this, and you can see the entire texture move towards the left. Similarly, you could move them on the y-axis. So let's just change the perspective, and now you can see we can move it on the y-axis as well. So all the points are moving in the y direction. And similarly, we can also move them in the z direction like this. Now that causes all of these to just move down, and you no longer get that shimmering effect because we are now in 3 dimensions. So in order to get that shimmering effect, you would have to change this from 3D to 4D, and now you can play around with the W slider. So again, you're able to move on the x-axis, you're able to move on the y-axis, which is front and back, and you're able to move on the z-axis, which is up and down. But apart from those, you can also move in the 4th dimension, which allows points to be randomly created and randomly removed as they move through that 4th dimension. So this is essentially the 3D equivalent of that 2D texture that you were getting, and the shimmering effect as you moved through the 3rd dimension on the 2D plane. Hopefully that wasn't a mouthful and too confusing, and is fairly simple to understand when shown visually like this. But that's all there is to understand in the 4th dimension. With this example, you can actually see that when we change this to 2 dimensions, you get these pillars because, just as I stated, the z dimension distance is completely ignored, so the distribution is only in the x and y plane, and the entire z axis gets the same copy, which is why moving on the z axis does absolutely nothing. But you can always move on the x axis as well as the y axis. So that is what this Voronoi texture does in 2, 3, and 4 dimensions. However, there is another thing that we did not talk about, which is 1 dimension. Now, again, many people do get confused when you switch something over to 1 dimension because the entire plane seems to have just one single color that is determined based on this W value. As you change the W value, the color becomes bright or dark. And that's because the W value by default is the 4th dimension. But you can actually control which one of the axes this W slider is by using the texture coordinate nodes and a separate XYZ node just like this. So if you connect the object, and now you get access to either the x-axis, y-axis, or the z-axis. So if you were to plug the x-axis into the W, you would see that the points are technically distributed along the x-axis, and the distance from each pixel to the point on the x-axis is what determines the brightness of the pixel. Because it's ignoring the y-axis and the z-axis completely, you get these straight lines along the y-axis. And you can choose this to not just be the x-axis, but the y-axis as well. And apart from just the x and the y, they can always be the z-axis also. But when you use the z-axis, it becomes very similar to just the w-axis, where you just get one single value for the entire plane, because remember, the points are being distributed on the z-axis, and we're only looking at the distance between each point and every pixel on the z-axis only. So everything on this plane should be equidistant from any point on the z-axis when considering the distance to the z-axis. So now if you were to move all the points along the z-axis, you would eventually reach areas where the point is intersecting with the plane, causing it to be completely black, and then it becomes bright again and dark, and so on and so forth. So that is what the 1D Voronoi texture actually does. So hopefully that gave you an idea of how you can use the first property, which is the number of dimensions that's being used to distribute the points and calculate the distances. The next property is the feature. property, and that is probably one of the most important properties of the Voronoi texture. Till now, remember, we were figuring out every pixel, the closest point, and then giving it a brightness based on the distance to the closest point. That, by definition, is the F1 feature, because we are finding the closest point. If we switch this over to F2, what it's actually doing is it's computing not the distance to the closest point, but the distance to the second closest point. So right off the bat, because we're finding the distance to the second closest point, the entire texture should become much brighter. Along with that, you will get a lot of spaces where the closest distance is far greater than 1, so you get a lot of these completely bright spots, where the value is just clipped off at 1 because the distance is so far away. But to actually see this or visualize it better, we can go ahead and do a few things. The first thing is we'll add back all of the points that were being used to calculate the F1 distances. So if we were to switch this to F1, you can see where every single one of the points actually are. Now, we'll keep the points exactly where they are, and we'll just switch this to F2. Now when we analyze it, you can see that for these pixels over here, the second closest point is actually very near to the first closest point, which is why they're still very, very dark. On the other hand, areas like this are very, very bright because the closest point is this, but the second closest point itself becomes very, very far. The second closest point is not really anywhere close, which is why the entire area becomes so bright. Over here, because 2 points are really close to each other, the second closest point is fairly close and it's dark. So essentially, any area where points are fairly close together, they get pretty much dark, and areas where points are isolated, like this point has no close neighbors, the entire area becomes very, very bright. So that makes sense for the distance output, but it becomes very, very visual when you use the color output. So right now, this might look like complete chaos, but let's go ahead and first off, look at what the points are when colored. So these are the points and the color of every single point for the F1 texture. So if we were to switch this over to F1 and take a look at it, you would not be able to see the points because all the points have the exact same color as these objects, but the points are present right over here. So if we were to now give the points these colors and just not look at the background, you can see how, okay, this point should be peach, this point should be this bluish color, this should be this purplish color. So let's go ahead and take a look at it. You see we do have this peach, this bluish, this purple. So all of the points are the correct colors based on the F1 distances. Now, when we look at these points combined with the F2 output, we can see the actual F1 points and their colors and how all of these are being shaded in. So if we take a look at this particular bluish dot, we know that all of the pixels present over here have this particular point as its closest point. And because this is the closest point, they cannot be this particular color. So as we go out, eventually at this point, we see that for all of these pixels, the closest point becomes this point. So the second closest point is actually this particular bluish pixel or this bluish point, which is why this area takes on that bluish point. So it's actually very simple to see. For this purple area, all of these areas have the purple point as the closest, and so none of these pixels can be that purplish color. Once we shift outside this particular edge, they end up becoming purple because now the closest point is the other point and the purple becomes the second closest point. So it's a lot like this particular cell gets unwrapped when we switch to F2. As you can see, just by looking at F2, we know that if we were to switch this to F1, this entire region should have become purple, whereas this region should have become this particular bluish color, and so on and so forth. You could actually find out that this area should have been gray, and it's that simple to figure out that we get this purplish area, bluish area, grayish area, and so on. So technically, if we were coding this shader ourselves, we could add in an F3, F4, which finds the third closest point or the fourth closest point, and so on and so forth. However, Blender just sticks to F1 and F2 for now. The exact same thing can be done for the position outputs as well, but we'll not go into too much detail because it's exactly the same thing. The next option is actually Smooth F1, which is also very self-explanatory. When we shift over to the Smooth F1, we get this new smoothness slider, which allows us to control how much the edges are going to be blurred out. So if you have a smoothness all the way to 1, the edges become very, very blurry as we smoothly transition from whatever color to the other color. But remember, this doesn't happen only for the color output. You could have the exact same for the distance output as well. Although the distance output is already a smooth gradient, the smooth F1 allows you to increase that smoothness by still blurring out the edges even more. So that's how you get these different variations for the smooth F1 as well. The next option is actually a very useful option, which is the distance to edge. Remember how for the Voronoi texture, we were finding each pixel, the feature point, and then finding the distance to the feature point. But the distance to edge actually inverses that entire operation. If we were to add in the original points once again, you can see what this does is from the point, it actually calculates what the edges of the color outputs were. So let's just switch this over to F1 and look at the color output once again. You can see that the color outputs had edges right over here, and similarly over here as well. Now, if we switch this to distance to edge, we see the exact same edges, but every single pixel is now going to calculate its brightness based on the distance or the shortest distance to any one of the edges, which is why everywhere along the edges it's completely black because the closest distance to the edge is 0 at the edge borders. However, as we move towards the feature point, the distance to the closest edge becomes more and more, so it starts getting brighter and brighter. And that is how we get this particular cell-shaped look when we use distance to edge. The last option is something that a lot of people get very confused by, which is the n-sphere radius. This seems to give a solid shading for every single one of the cells, which makes it look very similar to the color output of F1 except black and white. However, what this actually does is gives us a value for every single cell where if we take the feature point as the center of a circle, the output of this will give us the radius of the largest sphere that can be drawn without intersecting one of the edges. Hopefully that again wasn't too hard to understand, but let's take a look at that with a practical example. If we take a Voronoi texture and we simply check for the n-sphere radius and compare them and look at the output, you can see how we get these particular circles. And the circles will never overlap with each other. They will perfectly just touch at places, but there will never be an actual overlap. So that is the use of this n-sphere radius. It will create a situation where there's no overlap between different circles. If we were to see circles like this that isn't intersecting any other circle, we can know that it is definitely touching an edge of the original cell. So we can take a look at that as well. If we add in the original cells, you can see that this particular circle is touching the edge. If we add in the original feature points as well, you can see that the feature points are the centers of the circles. So you can see each center is right there, and the largest possible circle that you could have created without intersecting with any of the edges is this particular circle. So that is what this n-sphere radius option actually does for us. As I stated, it is the largest possible circle that can be drawn without intersecting the edge of each cell. Now, the formal definition might be a bit different, so I would suggest that you actually look at the Blender documentation to get a hang of the formal definitions. And that finally brings us to the end of the feature outputs. Next, we can look at what might just be the most interesting and informative part of this video, which is the next option for the distance metrics. So what even is a distance metric? So for now, when we were looking at any of these, we were seeing that we always had to calculate the distance from each pixel to the feature points. But the question is, how do we calculate the distances? Till now, the way we were calculating distance is finding the absolute distance, which is actually the Euclidean distance that we can see right over here. What exactly is the Euclidean distance? The Euclidean distance is the distance that we're all familiar with, which is where we have a point, we have another point, and we just measure the direct straight line distance between them. Now, if we were to actually take a look at this mathematically, we could do that as well. And for the sake of viewing things easier, let's just switch off the grid and maybe the plane as well. So if this is a point and this is the pixel that we're searching for, the points would have coordinates maybe x1, y1, and this point would also have coordinates maybe x2, y2. So the Euclidean distance between these is given by the distance formula, which you do study in high school math. And again, for completion, let's just write it down. The Euclidean distance is going to be equal to x2 minus x1, which is essentially this distance over here, and y2 minus y1 would be this distance. But let's just take a look at that in the formula. So x2 minus x1, and we have to square this, plus y2 minus y1 whole squared, and the entire thing would have to be underneath the root. And if you're actually wondering how this formula came about, it is actually from our very old Pythagoras theorem of a squared plus b squared is equal to c squared, which I'm sure a lot of designers would still remember from high school and would be thinking, where am I ever going to use Pythagoras theorem and trigonometry ever in my field of work? Well, in case you were wondering that, here you go. Pythagoras theorem is used to find the Euclidean distance, which is used to create your Voronoi textures. However, this is actually very similar to the equation of a circle, and that's why for the Euclidean distance, we always get circular textures. If we take our Euclidean distance and just start bringing in the black, you can see that we're always getting circular textures. And that is why you can use the Euclidean distance metric in the Voronoi texture to create circles. Another method of thinking about it is every point in a circle, on the circumference at least, is equidistant from the center of the circle. So that is the Euclidean distance metric. But how can there be other methods of calculating distances? Let's just go ahead and take a look at that. If we bring our grid and plane back and now switch this from Euclidean to Manhattan, we see that the texture completely changes. Similarly over here, let's just look at what it looks like in Manhattan. Now, to understand why we're getting this particular shape, let's go ahead and take a deep dive into each one of these pixels. Let's assume that each pixel is not a pixel, but a building in the city of Manhattan. If you want to find the distance between maybe this point over here and this particular point that we're searching for, we can no longer just go in a straight line. That is no longer possible because there are buildings in the way. We can't go through the buildings, so we have to follow the path around the buildings. And in order to do that, we would have to go down like this, and then like that, and like this, and that, and we'd have to just keep crisscrossing until we get to our point or our destination. That means we can only move in perpendicular directions. If we were to calculate the total distance, we would see that the total distance covered is going to be the summation of all of these vertical different motions and all of these horizontal different motions. So that would be this entire distance, which is the differences in x, and this entire distance, which is the differences in y, which can actually be represented as delta x and delta y, which is a little triangle. And the total distance is going to be this delta x plus delta y. Now remember, delta x is actually just x2 minus x1, and delta y is y2 minus y1. So this is the Manhattan distance. Again, for completion, let's go ahead and write that down in our little formula sheet, where the Manhattan distance is x2 minus x1 plus y2 minus y1. That's actually all there is to calculate Manhattan distance. If we actually look at the distance for all of these, we can see that for all of these points, we just have to move one block down and we get it. So all of these have a distance value of 1. However, for these 4 points, we can't just move diagonally down. We have to move only perpendicularly. So we'd have to move one step like this and then one step down, or one step like this, one step toward the left to get to our point. So we'd always have to move 2 steps. So this would have a distance value of 2, and which is why the corners are slightly brighter. Now for these values, you see we have to move once and then twice. So this has a value of 2, this has a value of 2, 2, and 2. Whereas for all of these, we'd have to move 1, 2, 3. So this has 3, 3, 3, 3, and so on. If we take a look at the next point over here, this one has to move 1, 2, 3, 4, or 1, 2, 3, 4. Either way, the minimum number of steps that this has to take is 4. So this is going to have a brightness value of 4, 4, 4, and that's how the entire pattern will continue all the way to infinity. Zooming in even further, we can actually see the values much better. So if we take a look at this, you see this diagonal will always be the brightest values, while these perpendicular directions will always have the darkest values. So because the perpendicular directions have to cross the least number of steps, they're always going to be dark, while diagonals are always going to be the brightest. So let's take a look and see if that is what is being represented on a larger scale. And also, let's just switch off the grid so that it's easier for us to see this. without the grid, it's actually very easy to see how all of these 4 have the exact same values, and then these have a values of 2, this and this are of the exact same value, which is 2, and so on and so forth. But when we zoom out, we do see that all of these get the darkest values, and as we go along the diagonal, they do get the brightest values. If we take a look at it over here, we do see the exact same behavior, which means that yes, we were correct. That brings us to the third option, which is Chebychev. Let's switch this from Manhattan to Chebychev. Now, the Chebychev directly, we can see, has these square-like shapes as we move around. How do we calculate the Chebychev distance? This time, instead of assuming this to be blocks that can't be entered, let's assume that these are tiles, and we simply need to calculate the minimum number of tiles that have to be crossed to get to our point. So if we were to get from some point like this to this point over here, we could simply jump to this tile, then jump to this tile, and then jump over. So this value would simply be 3. However, if we notice, to get from here to here also, we'd have to jump to 1, 2, and 3rd, which means this would also be 3. That is why the Chebychev distance always goes in a square-like pattern, where all of these have a value of 1, and then as we get to this entire border, they all have a value of 2 because we have to jump 2 tiles to get to our final destination point. Similarly, all of these will have a value of 3. If we switch off the grid, you can see exactly how these values are, and that is what the Chebychev texture looks like. However, although these diagonals are the exact same values as the square, because our brains are used to having it such that we see circular shapes to be equidistant, we'll notice that these edges actually end up being a value of 3 all the way out here. But if we go the exact same distance in this direction, it's actually much brighter. This area would have a value of 5. So because we see this is just 3 and this is 5, the diagonals actually end up appearing to be darker than the edges, although you can clearly see that is not actually the case. But when we zoom out, you'll start noticing that your brain does perceive these edges to appear darker than their counterparts, although we clearly see that isn't the case. These edges or these corners are the exact same color as the rest of it. But as we zoom out, they just appear darker to our brains because of the way we perceive things. If you go ahead and take a look at this shader, switch to Chebychev, we see that exact same behavior as expected based on what we said the Chebychev distance was. But again, for completion, what is the mathematical formulation for the Chebychev distance? The Chebychev distance is actually the maximum of the two. It's either going to be x2 minus x1 or it's going to be y2 minus y1. So whichever one is larger, the Chebychev distance is going to be that particular distance. Remember, this should have been x1. So essentially, as we're going from Euclidean to Manhattan to Chebychev, we simplify it quite a bit. If we take a look at this mathematical equation based on our example over here, you can see that for maybe these pixels over here, let's say this one, it is absolutely 0 on the x. The x value of this is also 0. The x value of this is also 0. So the difference between them is 0, but the y value is 1, and here the y value is 2, here the y value is 3, so the difference is going to be 1, 2, 3. So that's why as we go up, we always get this y distance to be calculated. As we move over to the left, however, over here, the differences in x and the differences in y is the same. Both of them have a difference of 2 because this point is 2, 2. As we move even further to the left, now the difference in y remains 2, but the difference in x becomes 3. And remember, when we say whichever one is greater, we don't look at x2 minus x1. In fact, I should have mentioned that we look at the difference between x2 and x1, which means we ignore negative signs. We just take the larger number minus the smaller number. So when we take the difference, it doesn't matter whether we get a negative number or a positive number, we just take the absolute value, and that absolute value, whichever one is greater, is what the distance is going to be. So I personally found this to be super interesting because when I initially started learning Blender, I always knew that in the Voronoi texture, we do have Euclidean, Manhattan, Chebychev, and we use Euclidean whenever we want circular or organic shapes, and we use Chebychev whenever we want sci-fi shapes. However, the last one is what confused me the most, which is Minkowski. The Minkowski distance metric actually renders the Euclidean, Manhattan, and Chebychev metrics almost useless because the Minkowski metric incorporates all of the other metrics. The Minkowski metric gives us this new option, which is called the exponent. If we change the exponent to a value of 1, you'll notice that this becomes the exact same as Manhattan. If we were to switch between Manhattan and Minkowski with an exponent of 1, we get the exact same thing with no difference whatsoever. Similarly, if we change the exponent value to a value of 2, you'll see we get the Euclidean distance metric. So there's no difference between Minkowski and Euclidean when the exponent is set to 2. Lastly, we can take the exponent and change it all the way to 32, and that should give us Chebychev. However, to actually get Chebychev, the exponent should be infinity, but it would be impossible for any laptop or computer to calculate or compute any value to infinity. So because we can't go all the way to infinity, we just approximate the exponent value of 32 to be equal to the Chebychev metric. Now, the only reason we still have Euclidean, Manhattan, and Chebychev is because it would be much faster for the computer to calculate these metrics in case you're not using the Minkowski metric. The reason why you would want to use the Minkowski metric is in case you want to transition between different metrics, as in something like the Manhattan metric to the Euclidean metric, or you want to use values in between the two where you don't want it to be completely Euclidean or completely Manhattan, but somewhere in the middle. However, what I had always used Minkowski for before I got to know this is reducing the exponent to values close to 0, like 0.3 or 0.5, actually gives us this sort of a star-like shape, which is what we always use Minkowski for, which is to create these stars. However, now you know exactly what the Minkowski metric is doing. We could go ahead and look at the actual equation for the Minkowski metric, but I think that gets a little too complex for the scope of this video and would require a little longer to explain. So let me know if you're interested in that and I'll create another video, as this video is already getting too long. So that's actually all the different distance metrics and what each of them does. Again, remember that you don't have to keep the distance outputs for different distance metrics. If you were to change to the color outputs, you would get different outputs based on the exact same Worley Noise algorithm where it's finding the closest point and it's shading in that pixel with that point, except to find the closest point, instead of using the Euclidean distance, it's using the Chebychev distance, which is why we get these particular shapes. The same thing works for Manhattan and Minkowski as well. Another very interesting thing to note is that although you learned these distance metrics in terms of 3D animation and motion graphics and Voronoi textures, they're actually not just unidisciplinary. That means you can use these same concepts in so many other disciplines, and one very interesting place in which these distance metrics are used is in machine learning. Many of the machine learning algorithms are based off of different distance metrics, and by learning this in terms of Blender, you can actually make use of it in those regions as well. So in case you're into AI and ML, you might come across this someday as well. Now lastly, let's take a look at this normalized checkbox. What this does is actually changes the range of outputs to go to 0 to 1 only. Remember, if we were to switch this to something like F2, we had these areas which are completely bright, and although areas over here should technically have a value greater than 1, we can't have a value greater than 1. So it just gets clipped off at 1 over here. When we press this normalize button, it essentially figures out what is the absolute furthest distance in this entire image, and it considers that to be 1, and it remaps from 0 to that old distance all the way to 0 to 1, which causes none of the areas to get clipped off. So that is what this normalize function does. It takes all of the values and pushes them down into a 0 to 1 range. If we were to go to F1 and you use this normalize button, you can see everything seems to get darker, which means that the furthest distance was still greater than 1 when it wasn't normalized. Sometimes you might have situations where the absolute furthest distance is not greater than 1, and then if you normalize, everything will seem to get brighter. In our situation over here, that isn't the case because everything is getting a little darker, which means the furthest distance was greater than 1, which is now being pushed down, and everything else is being adjusted accordingly. And with that, we actually finished all of the properties of the Voronoi texture. Now, let's move into the various inputs to the Voronoi texture. A few of these inputs do change based on the feature outputs and the distance metric, but we already went through those different inputs when we looked at them. For example, the smooth F1 gives a smoothness slider, and the Minkowski gives us an exponent slider. So let's not take a look at those, and we'll just look at the generic ones. The first one is the vector input. Now the vector input is common to any texture in Blender, so we're not going to spend too much time on it. However, you should know that you can connect them to a mapping and texture coordinate node, which allows us to actually change the location or position of any one of these textures. Along with that, you can rotate them as you want, and you can also scale them up and down accordingly. But since they're the same for every single texture, we'll not spend too much time on it. The next is the scale, which again is generic for almost every texture, where you can actually scale up to give a zoom out effect, and we can scale down to create a zoom in effect. Now, exactly why that happens can be saved for another video, so again, let me know if you would be interested in watching that. The next three are probably the most important and the most misunderstood: the detail, the roughness, and the Lacunarity values. The Lacunarity value is actually something that came newly in Blender version 3.6 onwards, so I think you would require either Blender version 4 or 3.6 to get this value in the Voronoi texture. The value has also been introduced to the noise texture, which has replaced the previous Musgrave texture. So let's go ahead and find out what these three do, because they are very closely dependent on each other. Changing just the detail or just the roughness will do absolutely nothing if the Lacunarity is set to 1. Similarly, if the roughness is set to 0, we can change the Lacunarity and the detail all we want and we'll get no change whatsoever. And just like that, if the detail is 0, the roughness and the Lacunarity has no effect on the final output. So they're very interdependent, but what do each of these do? Let's start by looking at the detail slider. What the detail does is it determines how many octaves are being calculated while calculating the Worley noise. Remember, each octave is like a new layer, so it's essentially calculating a number of layers. So we can visualize that by adding in different planes just like this. So if we imagine a very high detail, we get many layers, and if we imagine a lower detail value, we actually create fewer layers. So lesser detail implies lesser layers, and higher detail implies more number of layers that are being computed. So greater detail will definitely take longer for your computer or Blender to actually calculate. Now, please note that all of this is just for visual representation, and obviously just changing the detail is not changing the number of layers over here. It's just giving a representation of what's happening. Now that we understood detail, we can take a look at roughness. Now remember, the final Voronoi texture output is going to be the summation of all of these different layers. We can assume that each layer has some amount of effect to the final image, and all of the different layers are being added together to create the final image. So what the roughness does is it actually calculates how much of an effect the next layer has in creating the overall final image. So if we have a roughness value of something very low, like 0.1, every adjacent layer will have 0.1 times the effect of the previous layer. Or in other words, it would have 10% of an effect while being added to the previous layer. So it would look something like this. So you can see, although all of the different layers are there and we have a very high detail of 15, because the roughness is very, very low, the second layer itself becomes 10% of the first layer, and the third layer becomes 10% of the second layer. And so by the time we reach the fourth layer, there's just such less brightness in any of it that it's almost ignored, and it doesn't have any effect in the final output. So as we start increasing the roughness value, we start giving each adjacent layer more and more power or importance in creating the final output. So it becomes something like that, where the next layers are getting more and more prominent. But till now, even if we have a very high detail and a very high roughness, when we actually look at it from on top, we should see absolutely no change, and that is because of the Lacunarity value. But before we get to Lacunarity, I'd like to say that if we have a roughness of 1, all of the layers will have the exact same importance or weight while being added up to create the final image. But for now, let's just keep that low and start thinking of the Lacunarity value. Now, traditionally, Lacunarity is derived from the word gap, and it refers to the gap between these various layers. Why does that matter? If we take a look at it from the top view, but we don't look at it in an orthographic perspective, you can already see how the different layers seem to get smaller as they go lower and lower. And that is simply because as things move away, they seem to get smaller. That's why when we add up the different effects, you can clearly see what sort of an effect it's creating in our final image. Let's go ahead and just make all of these have the same brightness, So now we can see exactly what is happening when we add up all of the different layers. We get this sort of an effect. However, let's go ahead and play around with the gap between all of these layers. So we can simply do that like this, where you can see we're actually going to start increasing the gap and decreasing the gap. So let's just look at what that's doing to the final image. So right now, if we take it and we just start increasing the gap, you can see how everything seems to change and become more elongated. Similarly, we can reduce the gap to reduce the effect, which would make it look something like this. So hopefully you're able to understand how increasing the gap causes these different effects. But remember, we don't have to stop reducing the gap at a value of 0. In fact, we can bring it such that we get it to a point where all of them lie on the same plane, so they look like they're all contributing to the exact same image, but we can actually move them towards the camera as well, which would cause this sort of an effect. That would make every adjacent layer seem like it's being scaled up instead of scaled down, as we were seeing in the previous example. So that's also a possibility that can be controlled using this Lacunarity value. However, Blender doesn't create it like that, where it considers it as the gap or the distance between these. Instead, Blender assumes that all the layers are always in the exact same position, just like this, where they're all in the exact same plane. However, what Blender does is it assumes this Lacunarity value is equal to the scale of every adjacent layer. So it actually takes the layer and just scales the adjacent layers down to either scale it up or scale it down to create every adjacent layer. So now let's just actually take a look at what each of these do without having our actual example, but we'll keep all of that in mind and take a look at this Voronoi texture as we play around with these Lacunarity, detail, and roughness values. So this is what the distance output currently looks like. With the Lacunarity value of 1, every adjacent plane is not being scaled up or being scaled down, which is why we get the exact same, and the roughness and detail mean nothing. However, if we were to slowly increase the Lacunarity, the scale of every adjacent layer becomes smaller and smaller, so you can see how we're getting that exact same zoom in effect. Let's keep the Lacunarity at something very, very small. Let's keep it at maybe 1.05, and let's start by reducing the roughness. As we reduce the roughness, you can see that it seems to be the exact same, but as we add in some roughness, the adjacent layers start getting in some value. So now you can see maybe 2 layers have quite a bit of an effect, and the third layer is almost non-distinguishable. But if we increase the roughness even more of the layers become more and more prominent while adding to the final image. However, if we were to reduce the detail, even if the roughness is all the way to 1, because the detail is only at 1.2, only 2 layers is going to be computed. And both layers have full 100% effect while creating the final effect. If we reduce the roughness, you can see the second layer is only half as bright as the first layer, and if you reduce it all the way to 0, the second layer is not even there. So roughness of 0.5 means the second layer is half as bright as the first layer. A roughness of 1 means both of them are equally bright. We can actually take a look at these two lines to take a look at it. This is actually the second layer. A roughness of 0.5 is causing it to be half as bright. I'm not sure how well it's visible on YouTube, but you could try this out yourself. Now, as we start increasing the detail, we're able to get, you can see the third layer being formed, and slowly the fourth layer, the fifth layer, and so on and so forth. So that is how these different layers are being formed, and the Lacunarity value determines how small the next consecutive layers are. If we were to start increasing the Lacunarity, the next layers become so small that they eventually become their own thing, and you can clearly see how we do have the original layer, which gives us these dark spots, and if we zoom in, we have even smaller spots. If we zoom into those spots as well, we get even more smaller spots, because that's how much each layer was zoomed in. Apart from that, we can have Lacunarity values lesser than 1, where each corresponding layer is going to be scaled up. And again, the detail and roughness does the exact same thing, where roughness gives us how effective each adjacent layer is, and detail determines how many layers are going to be computed. And just like every other property and every other input, it doesn't have to be just the distance output. You can get the exact same thing for the color output as well as the position outputs. So it's really worth playing around with these to get a sense of how you can see each individual layer is being zoomed out or zoomed in. In fact, it's much easier to see with the color output. It's being zoomed out and it's being zoomed in just like that. And again, you can see how light this layer is. If we were to increase the roughness all the way to 1, the first layer is essentially just as bright as the last layer, and the image is a summation of all of these layers. If we start reducing the roughness, these layers become very, very light as compared to the original layer present over here. Similarly, we can increase the detail to increase the number of layers that are present. So hopefully that clarifies what the detail, roughness, and lacunarity values actually do. The last thing that we have is the randomness, which simply determines how random the position of the points are. If we take a look at the original Voronoi texture with all of the feature points, by just reducing this randomness, the points actually come into a perfect grid-like pattern. Now let's go ahead and move the points as well. And that is what happens. Increasing the randomness simply changes the randomness or the position of these points to a more random location. Let's drive both of these using a single value so that they move together, the points as well as the texture. So you can see that you're able to increase the randomness, but it clamps off at a randomness of 1. And just like before, it does not have to be the distance output. It could be the color and all of that. The randomness simply changes where the points are present. So that's actually all there is to figure out from this particular node. So that gives us an overview of all of the outputs, properties, and inputs to the Voronoi texture. Remember, you can always mix and match between all of the different settings that we looked at to get various results, but not just that. You can also combine different Voronoi textures together to get even more sci-fi textures and abstract textures as well. There are many tutorials on my channel, such as this tutorial over here, which implements a combination of Voronoi textures to get different results. So if you're interested in learning how to create different materials with the Voronoi texture, definitely check those videos out. Apart from that, if you liked this video and you learned something from it, let me know down below if you'd want to see more videos of this style where we take a deep dive into different nodes. Blender is a very extensive software and there's so much to learn about every single one of the properties, and I intend to help everyone understand the software even better. So do let me know if I should create more videos of this style, and if you watched this far, thank you so much for watching. You're probably in the 1% of people that actually watch this video. Until my next video comes out, you can definitely check out other demystifying videos or tutorials based on what your preference is. Until then, thank you so much for watching, keep creating, and don't forget to stay creative.